It's a real pleasure to have to introduce Dr. Nihan Pol. So Nihan is a VIDA postdoctoral fellow at Vanderbilt. So VIDA actually stands for Vanderbilt Initiative in Data Intensive Astrophysics. So he's working with Steve Taylor and his collaborator on developing methodologies to hasten the discovery of nanohertz gravitational waves and exploring what kind of astrophysics you can extract, during the IPTA era of gravitational astronomy. Nihan graduated. Nihan is actually from Pune. He graduated from West Virginia last year, working essentially closely with Maura and Dang, essentially working on nanohertz gravitational wave related topics, as well as testing GR using binary pulsars, especially a possible way to extract the moment of inertia in the case of double pulsar, and then doing population synthesis to constrain extremely short period compact binaries like neutron star wide dwarf, somewhere in the 15 minutes kind of period, which has implication for LISA and SKA era. And of course, as I mentioned, he's one of NANOGrav young talents trying to hasten the discovery of nanohertz gravitational waves. I think today is going to talk about why IPTA will be crucial to realize gravitational astronomy in the coming years. And I will, after this introductory words, I'm handing over to Nihan. Nihan, please.
Thanks for the wonderful introduction, Goku, and thank you for inviting me to give a seminar here at DIFR. I really appreciate it. I'm going to share my screen, and could you confirm that you can see it?
Oh yeah, very well, clear.
Okay, awesome. Again, thanks for the introduction, and just a quick notice is that I'm going to turn my video off just to avoid any unforeseen problems, but I can turn it back on once we get to questions at the end. Right, so today I'm going to be talking about astrophysics milestones for PTA gravitational wave detection. And this analysis was really inspired by the really exciting results that we saw coming out of the NANOGrav 12.5-year analysis. So to give you a quick overview of how the talk is going to go out in the next hour or so, I want to start off by revisiting the NANOGrav 12.5-year results that Steve talked about last week. But I just want to give everyone a refresher just in case people here weren't at that talk. I then want to talk a little bit about how we can go about inferring the source of the gravitational wave background given a detection of the background by any of the PTA detectors. Then I will spend a little bit of time talking about how we go about simulating realistic PTA datasets, and then how a gravitational wave background signal will actually evolve and manifest itself in a PTA dataset. And then finally, I will end by highlighting the importance of the International Pulsar Timing Array collaboration, or IPTA for short, and show that it is indeed the way of the future, and it can get us to the science that we can do with pulsar timing arrays much quicker than would be possible with any individual PTA. So to start off with, I wanted to talk about the NANOGrav 12.5-year analysis. And in particular, the results that we saw coming out of the stochastic gravitational wave background analysis. So recently, NANOGrav reported the presence of a spatially uncorrelated common process in the 12.5-year dataset. And by common process, I mean that this signal was common to a majority of the pulsars that are included in that pulsar timing array. So on the left-hand side here, I'm showing the frequency, the observed gravitational wave frequency on the x-axis, and the delay that's induced by this common process in the dataset on the y-axis. The gray violin plots themselves are the result of what we call a free spectral analysis, or a full spectral analysis, which is kind of the most general type of analysis that you can do with a PTA gravitational wave detector. So in this type of analysis, what we do is we do not assume any kind of model for the gravitational wave background, but rather we model all the different frequency bands independently. So what this gives us is the gray violin plots shown on the plot on the left. And we can see that the common process that we are seeing in this 12.5 data set is manifested only in the lowest couple of frequency bands. And if there was no signal at all in this data set, we would expect all of these violin plots to be roughly flat, as we can see here at higher frequencies. So once we get past this sort of general way of searching for a background in our data set, we can also parameterize the background by any model that we want, really. But the simplest model for the background that we can use is a power law, right? And since we are seeing this common process in just the lowest few frequency bands, in this analysis, we first looked at just fitting a power law using the lowest few frequency bands. And that's what's shown by the dashed orange lines. However, since it's standard practice in PTA detection, we also did a corresponding power law fit, which used all 30 frequencies in the PTA detection analysis. And that's shown in the green dashed dot lines. And finally, we also did a broken power law analysis, which allowed the power law to have a steeper spectral index at the low frequencies and then flatten out to a spectral index of 0 at the higher frequencies. So kind of the best of both worlds between 5 and 30 frequencies. And so the result of this analysis was that the spectral index of this common process that we are seeing is very poorly constrained right now. So the corresponding two-dimensional posteriors on the amplitude and the spectral index are shown on the plot on the bottom left. And like I said, we can see that the spectral index is fairly unconstrained at this point. But the sort of expected source of the background at nanohertz frequencies is expected to be a population of inspiraling supermassive black hole binaries called SMBHBs. And it's a fairly well-known theoretical result that we expect this population to produce a background with a spectral index close to 4.33. And so if we take a slice at that spectral index, we get a median amplitude for the background of about 1.9 times 10 to the minus 15 in the 12.5-year analysis.
Yeah. Previous plot. So what is the vertical line? Can you remind us? I forgot if Steve mentioned that.
In which plot? On the one on the left, on the top left or bottom left?
Yeah, both. What are you? So yeah, top one. What is the vertical line?
Right. So in the top plot, the vertical line represents a frequency of 1 over a year. So that's around 32 nanohertz. And on the plot on the bottom left is it just represents a spectral index of 4.33. So it's showing the slice that we take across the two-dimensional posterior.
Okay. And so what does the sensitivity curve of this kind of analysis look like, or the noise plot?
So that's the one that's shown on the top left, where we see the common process emerge at the lower frequencies and at higher frequencies.
This is the but what will be the noise if you plotted the sensitivity curve? What will it look like? Do you have that plot?
I do not have it with me, but if you think of
where is the minimum? If I remember, it goes up at low frequencies as well as high frequencies, and then there is a sweet spot. So
yes,
where was the minimum?
Yeah, that is correct. And so it's essentially showing the same information that's plotted in the plot here on the top left, wherein your high frequency end, which sort of goes up, is dominated by white noise. But that plot is just represented in terms of the characteristic strain, whereas here we are showing the delay produced in the timing residuals. So it depends on how you model the sensitivity curve, and it's at this point it's slightly hard to get the sensitivity at these low frequencies. But I do have a sensitivity curve towards the end of my talk for IPTA and NANOGrav 9 years. So hopefully we can.
It is always suspicious when your signal emerges just when your sensitivity starts to become bad. You know, that might be a signal from some systematic or some unknown.
This is unlikely to be that, because so So the noise floor at these low frequencies comes from the fitting of the derivative of the period for these pulsars. And that's expected to be much lower than what we are seeing here. So that's expected to be around a few nanohertz or a few tens of nanohertz, right? Yeah. And that's just much smaller than the signal that we are seeing here. So it's unlikely to be that. But there are other ways that we can go about testing whether this signal is astrophysical in origin, and I'll talk about that in a few minutes.
Okay.
I have one more question. This is Amol here. So I'm not in the area, so I wanted to take you slightly backwards. Can you give me some idea of what exactly is measured when you say a common process delay?
So what I mean by a common process is a signal that is present in all the pulsars in the pulsar timing array on top of any other noise process that might be present in the pulsars in your pulsar timing array. So remember that the common process literally has to be common to all or a majority of the pulsars in your array. And does that answer your question?
The first part, yes. The second is, of course, what exactly is measured when you say the CP delay is measured?
Right. So fundamentally, what we're doing is we are measuring this extra delay that's caused in the timing residuals. And so that's what's shown on the plot on the top left, right? So if it was just white noise in the data set, like I said, the violet plots would essentially be flat. But we are seeing this extra unexplained delay in our data set that can be explained by the presence of this common process.
So this delay,
fundamentally the quantity that we are looking for is this extra delay in timing residuals.
So I think Amol was not maybe in the last talk. So he's asking what is observable.
So delay is compared to what? Let me clarify.
As arrival times of pulses, right?
Yes. So you typically have a timing ephemeris or a timing model for every pulsar. Okay. And in all of these, and in this model, you account for all of the sort of modeling the pulsar spin, modeling the pulsar's orbital parameters, and modeling any kind of ISM noise, interstellar medium noise that might be present. And on top of that, once all of that has been modeled out, on top of that, what we do is we search for any extra red noise process. So a process that has a very long period in these pulsars. And we don't just search for it in one single pulsar, we search for it across all of these pulsars, which is why it's a common process.
Thanks.
I think there is one more question. I think it's from Ambarish. Ambarish, please go ahead.
Yes, can you hear me?
Yeah.
So I'm sorry, I don't exactly understand this figure, the top one. So you are plotting these gray violent, you are mentioning about these gray violent plots. So they are some vertical patches. So how to read them? So for example, for a particular frequency, they span a range of CP delay. So how to understand them?
Yeah, that's a good question. What the gray violence themselves are showing is the spread of the posterior of the delay recovered at that frequency. So for example, if you look at the lowest frequency bin, then this is essentially showing you the width of the posterior that's recovered from the Bayesian analysis as to what the common process delay is induced in this frequency bin. And that's the same for all of these other violets.
Okay, thanks. So essentially you are measuring the CP delay on some particular frequencies only, and these are okay, so it's not a continuous curve, right?
Yeah, it's not a continuous curve. So the lowest frequency bin is chosen such that it's 1 over the observing baseline, and then your frequency spacing, so your maximum frequency that you can search up to is dominated by a Nyquist sampling. But we typically don't go to such high frequencies. We usually use just the right number of frequencies such that adding any more frequency bins does not really improve your inference of the signal. And that turns out to be 30 frequency bins, which is shown here on the top left.
Thanks.
Okay, awesome. And yeah, please feel free to interrupt me because I'm sharing just the one screen that I have and I can't really see if there are any raised hands. So please feel free to jump in if you have any questions. Right, so moving on. So we have this common process that's emerged in the 12.5-year data set. But the key thing to remember is that even though the base factor for the presence of this common process over just independent red noise in each pulsar is greater than 10,000, so there's overwhelming evidence for the presence of the common process, there's still no statistically significant evidence for the presence of quadrupolar Hellings and Downs correlations in our data. And by what I mean by this is that the quadrupolar Hellings and Downs correlations, or HD correlations, is considered to be the smoking gun signature of an astrophysical gravitational wave background. And so on the figure on the top left here, I'm showing in the black points are the bent cross correlations as a function of the angular separation of the sky. And in the blue dashed line is shown the theoretical Hellings and Downs curve that is expected for an astrophysical gravitational wave background. And so we can see that while it seems okay-ish, it's not the best fit to the cross correlations that we are seeing in the dataset. And instead, it can be much better explained by just a simple constant line fit, which is referred to as a monopolar fit. And this corresponds to clock or GPS offsets. So using these cross correlations in our dataset, we can compute the signal to noise ratio in these different types of spatial correlations in our dataset. And that's what's shown on the bottom left. And like I said, we can see that the Hellings and Downs correlations are not at all significant. And by significant, I mean they are much below a value of 3, which is typically considered to be sufficient evidence for the presence of a Hellings and Downs correlated process. So in the 12.5-year data set, the signal to noise for Hellings and Downs correlations is around 1. And so it's really nothing to write home about, and certainly not high enough to claim a detection of the gravitational wave background. So why Hellings and Downs correlations? Why do we place so much importance on this specific type of cross correlations in our data set? And the reason can be explained by this great analysis that was done by Tiburzi et al. In 2016, where what they did was they looked at different noise processes that can exist in any PTA dataset, and they looked at what type of spatial correlations those noise processes can generate in any given PTA dataset. And so that's so a subset of the results is shown here on the plot on the bottom, where the x-axis, which I apologize is being cut off here, but the x-axis is the same as what we saw on the last slide, which shows the angular separation on the sky, while the y-axis represents the cross correlation values. And what they found in Tiburzi et al. Analysis is that the only process known to produce quadrupolar Hellings and Downs correlations is the stochastic gravitational wave background. No other type of process can actually go and create this type of quadrupolar correlations in PTA datasets. And so an example of the Hellings and Downs correlations is shown in the panel on the top. So the left-hand column shows the correlations in one particular realization of their simulations, while on the right-hand side, it shows the average of these cross correlations across hundreds of realizations in their analysis. And so the top row shows the Hellings and Downs curve generated by a gravitational wave background, while the other three panels show different types of noise processes. So the first one, UTN, so the second, which corresponds to the second panel, shows just uncorrelated independent timing noise in all the pulsars in your dataset. And you can see that these don't really produce any kind of discernible cross-correlation pattern. Similarly, like I said in the last slide, clock errors or GPS offsets in your PTA data calibration can produce a constant offset called the clock or monopole type correlations, and it's essentially just a constant horizontal line. And finally, ephemeris errors, which correspond to mismodeling of the solar system barycenter, can produce a cross correlation in our dataset that looks kind of like a cosine wave. And just to reiterate, none of these other noise processes can produce a quadrupolar quadrupolar cross correlation in our dataset. And that is really key to why we base the claim of a detection of a gravitational wave background on the Hellings and Downs cross-correlation signal-to-noise ratio. So given all of this, and having said that—
Can I just ask a question on the base factor again? So I guess when you say 10,000, right, what is the null hypothesis? There is no common process?
The null hypothesis, it's partly that, but to state it more formally, it's that the null hypothesis is just independent red noise in the individual pulsars in the PTA.
Okay. And just one more comment. I think so there was a paper about a month ago that what some caveats with the base factor, which argues that one should also consider fluctuations in the base factor, and a base factor itself is a stochastic variable. So I don't know if I mean, this was in the context of cosmology which this was used to assess the tension, but maybe at some point you might look at that also. So this is a paper by Chokami et al. Last month. Just a comment. So.
Yeah, that's an excellent point. And yeah, so two things. We definitely are thinking about that. And I'm leading a simulation team with the NANOGrav right now, where we are trying to see how often we can produce signals with this level of significance just out of random uncorrelated noise in our pulsars. So we are definitely looking at that, and we understand that we need to quantitatively show that it's really unlikely to get such high base factors. So yes, we are completely looking at that, and I will definitely look up the paper that you just mentioned. All right, so given the caveats around the 12.5-year data set, and that we cannot really claim a detection of a gravitational wave background at this point yet, given the lack of the Hellings and Downs cross-correlation signal-to-noise ratio, we can still go about using the two-dimensional posteriors to try and infer the source of the gravitational wave background under the assumption that the signal that we are seeing will eventually be confirmed as a gravitational wave background in future data sets, either from NANOGrav or from other PTAs. And so, like I said, the primary tool for inferring the source of the gravitational wave background are the two-dimensional posteriors on the gravitational wave background amplitude and spectral index that I showed earlier. And here I'm showing one of these interpretation papers that followed the publication of the 12.5-year analysis, where what they did was they took the two-dimensional posterior that was released in the 12.5-year analysis, shown here in the plot on the left as the black dashed lines. And what they did was they simulated a bunch of Monte Carlo simulations of different supermassive black hole binary populations, and they showed that different populations of these systems could indeed produce a signal that's consistent with what we are seeing in the NANOGrav dataset. And so those the posteriors that they produced from their Monte Carlo simulations of supermassive black hole binaries is shown by the contours in the green, and the vertical red dashed line represents that theoretical 4.33 spectral index that was derived by Finney in 2001.
So Nihan, what determines this spectral index? Is this the mass function of the binary black holes?
I'm sorry, could you repeat that again?
So what determines this spectral index? Is this the mass function of the binary black holes?
The spectral index of 4.33?
Yeah.
No, so the mass function is one aspect of it, but there's a lot of other things that go into this, and you also have to look at the number density. You need to look at the evolution of these supermassive black hole binaries over their lifetime, particularly how quickly, or you need to look at how the supermassive black hole binaries are coupled to their environment, how quickly they can sort of collapse down to these milliparsec scales where they can begin to, where their orbital decay begins to be dominated by gravitational wave emission, which is what we are actually seeing with PTAs. So it's a whole host of quantities that go into it. And if you want to look at it in more detail, I would recommend going to this Middleton et al. 2021 paper.
Okay. And will you show the power spectrum, the actual power spectrum also? Or I'm assuming it will not be exact power law, right? There will maybe. So
yes,
measured at probably per one particular frequency.
Not quite. I'll get to the spectrum in a couple of slides.
Okay.
And then we can revisit this if you want.
Nihan, the deviation is coming. I mean, Finney's analysis assumed that this is circular.
Yes.
So that, are you saying that, but the deviation need not come from, if you make it spin and eccentricity and other things, that will not change that much. That was my impression. It may change the amplitude, but
yeah, that's right. But what Finney assumed was that the complete evolution of this supermassive black hole binary is being driven just by gravitational wave emission, when we know that that's not true, right? So there's a lot of environmental coupling effects that come into play. There's the orbital configurations of the population. So for example, if you have really high starting eccentricities for this population, then that can again sort of produce deviations away from the theoretical 4.33. And again, finally, this is, so in deriving the Finney result, he also assumed just a continuous distribution of these sources in the local universe, where we know that that's not quite true. There's finiteness in the population, there's discreteness in the population, and that can also kind of produce this posterior spread around 4.33. But again, notice that the green posteriors that they produce in this analysis are still centered on 4.33. So that's
precisely.
Yeah.
Yeah. Okay, thank you. I will take a look at this paper. Yeah.
Mm-hmm. Right. Oh, sorry, go on.
Oh, okay. There's a question from Kato. Is it possible that other correlation curves would have a larger base factor? Which I presume he was referring to the monopole contribution, which indeed had a higher base factor, right? So
yes,
you can actually rule it out then that way. Yeah.
Yeah, that's exactly right. And so given the 12.5-year data set, since we see that the monopole is a better fit, you can see that it indeed has a higher cross-correlation signal-to-noise ratio than the Hellings and Downs correlations, which are around 1, while monopole is around 2.5. And so as the signal evolves, which I'll get to later in my talk, we will actually see the significance in the Hellings and Downs correlations grow, while the significance of the other two types of correlations shown here kind of stays flat. And so I'll get to that a little bit later in my talk. So that was one of the central things that we did in this analysis. But yeah, that's a good question.
Please go ahead.
Right. So just to summarize, the point of bringing this slide up was that we can use the two-dimensional posteriors on the amplitude and spectral index that come out of our PTA detection to try and infer the source of the gravitational background. And so here I've just shown one particular study that looks at supermassive black hole binaries, just because that's the most popular model that's expected to produce this background. However, that's not the only model that has been proposed to produce this kind of background. And there's a whole list of other models that have been proposed. And we literally have more than 100 citations on the 12.5-year analysis, where each one of them has a slightly different flavor of some of the models that they're proposing. And so some of the more exotic models that have been proposed as an explanation for the 12.5-year signal are cosmic strings, primordial black holes, inflation, first-order cosmological phase transitions, among, just to name a few. And I just want to say that I'm absolutely not an expert in any of these, and I would highly recommend that you go and follow these papers that I've cited, or just look at the citations for the 12.5-year analysis paper, and you'll see a really great resource for just following up with all of these. But this is just to drive home the point that we can use the two-dimensional spectral index and amplitude posteriors to infer the source of the gravitational wave background. So what we would want to do in terms of predicting where PTAs are going in the future is to show how the accuracy on the spectral index and the amplitude of the background will evolve as a function of time. And that is something that we do in this analysis.
So Nihan, do you remember for primordial black holes, how different is the spectral index?
It depends on what model you're looking at. So I know there's models that predict spectral indices of, what was it? They tend to be higher than 4.33. I unfortunately don't remember the numbers off the top of my head. But like I said, it's heavily model dependent.
Okay.
Right. So once we are fairly sure about what the source of the gravitational wave background is, we can sort of move away from this simple parameterization of the gravitational wave background as a simple power law and try to extract the full spectral information that's constrained in the gravitational wave background signal. And what I mean by that is doing this free spectral or full spectral analysis that I showed in the first slide of this talk. And just to give an example of what kind of spectral information can be encoded in the background, I'm again coming back to this example of the background which is produced by supermassive black hole binaries. So some of the information for a background produced by supermassive black hole binaries is information about the orbital parameters of the population. So in the example on the left-hand side, I'm showing the effect of having the supermassive black hole binary population start off with really high eccentricity. So in this example, it's an eccentricity of 0.75, and then these systems are allowed to evolve over time. And the authors in this case, Kelly et al. In 2017, they then calculated what the spectrum of the gravitational wave background produced by this type of a supermassive black hole binary population would look like. And that's what's shown on the left-hand plot. So in the blue is the theoretical Finney et al. Curve, which is shown with the typical 4.33 spectral index, which in this particular representation of the strain space corresponds to a spectral index of -2/3. However, if your supermassive black hole binary population started off with this really high eccentricity, then what happens is that this induces a turnover, a low frequency turnover in the spectrum of the gravitational wave background. And so as PTAs begin to probe these lower frequencies, as the baseline of the PTAs increases, we are actually able to search for the presence of any kind of spectral turnover in the gravitational wave background spectrum. And a similar type of turnover can be produced by environmental coupling effects in the supermassive black hole binary evolution, and just the evolution of the black hole binary in general, right? So in addition to just producing this spectral turnover, what's also interesting is that because this population of supermassive black hole binaries is indeed finite and it's not a fully continuous uniform distribution, what happens is that the real spectrum that's going to be produced by these supermassive black hole binaries is not going to be this smooth curve that we are typically used to seeing. There's going to be some amount of
Nihan, if I may interrupt, I'm Bhalchandra Joshi. So if you can just go back to the previous slide, could you explain in the red dashed line what is the source of that kink at the low frequency? So there seems to be a kink there at around 10 to the power -3. Can you explain what is the reason for that kink?
I think that kink is because that's where the environmental couplings in this cosmological hydrodynamical simulation kick in. But I'm not 100% sure, but I think it's where the high eccentricities are coupled with environmental coupling effects like stellar hardening and disk effects. I think that's it, but I'm not 100% sure.
Okay, so it's some kind of a late dynamical coupling between the gas and the stars in the binary system. Is that one possible explanation?
Yeah, absolutely. I think that's what it is.
Actually, if something is happening very late, will it not appear at shorter frequencies later in the evolution? I would think the earlier in the evolution is small frequencies, and later in the evolution will be high frequencies when the orbit is becoming closer.
Yeah, you're absolutely right. This is relatively earlier times. So yeah, these would be periods of about 1 over 100 years, right? Or 100-year period.
And then you're saying if you started with a circular orbit, then you will not see these kinks. Is that the claim?
Yeah, that's how. Yeah, that's exactly right. That's how Finney derived his results, where he assumed just purely circular binaries, where you have the entire evolution driven by just gravitational wave emission, and then that's when you get the blue dashed curve. So then you would not see this turnover.
So the way of thinking about is that in the circular case, all the power is in the second harmonic. I mean, so you're thinking about lots of binaries at various frequencies. Whereas here, if you take a binary, the energy in the gravitational wave is sort of distributed, and that's why it's bringing down at a given frequency the strength, and that's the way to think about it.
Yeah, that's also right. Right. So, like I was saying, in addition to not being, in addition to the turnover, the spectrum produced by supermassive black hole binaries is not going to be this smooth looking curve. It's going to be really bumpy because of the finiteness of the population, and that's also that's also to some extent a deviation from a pure power law. So we can expect to see these kinks and bumps manifest in our full spectral modeling of the gravitational background.
Nihan, so there we are not thinking about terminating the evolution, right? Or this is something else, right?
I'm not sure what you mean.
See, all the evolution so far they have been talking about is considering these binaries are essentially moving along Newtonian orbits.
Yes, I think so. Yeah.
But there are relativistic effects will walk in at some point of time. So the high frequencies we may have to be careful.
Yeah, absolutely. And this is so the point of this is not really to concentrate on or bring the focus onto like individual binaries that might pop out of the background, right? So this is more a statement about just the form of the spectrum that we should expect, and that it's not going to be like a pure power law. But you're completely right in that once we get to these higher frequencies, there's going to be more relativistic effects that we need to worry about.
Yeah, thank you. Please go.
Right, and so one final thing that I want to bring up really quickly is that since this is a background that we're going to be detecting, we do expect there to be some level of anisotropy in the background, and this anisotropy is going to encode information about the underlying demographics and finiteness of the supermassive black hole binary population. And in addition, what might happen, depending on whether we live in a favorable universe or not, we might see some bright binaries appear as bright point sources on top of the gravitational wave background that we just talked about. And these might become apparent in these anisotropy maps that we can make with PTA datasets. And an example of a simulated background with a few bright sources on top of it is shown here on the left from the analysis by Taylor et al. And however, even if this anisotropy might exist in the nanohertz background, unfortunately, we need really high values of the Helens and Downs cross correlation signal to noise ratio to be able to start detecting the anisotropy with any amount of statistical significance. And so that's what's shown here on the plot on the left, where on the x-axis we have this Helens and Downs signal, cross correlation signal to noise ratio. And on the y-axis, we have the Bayes factor that's in favor of anisotropy over just simple isotropy. And we can see that just to get to Bayes factors of around 10 in favor of anisotropy, we need signal to noise ratios in the Helens and Downs correlations of close to about 20 or so. And that's really high. And just to remind you, right now, the signal to noise ratio in the NANOGrav dataset is around 1. So that tells you how much evidence we need to accumulate before we can even begin thinking about looking for anisotropy of the gravitational background.
Nihan, so this analysis, again, I have not looked at this paper carefully. So you assume that this isolated binaries are emitting only one frequency, right?
Yes, that's right.
And we don't even consider the pulsar terms in this analysis either.
Yes, that is correct.
Okay, thank you. But that can, in principle, change, right? Is there any reason why, so the pulsar terms can actually make a slight, different
Sorry, Gopu, what are pulsar terms? Can you explain?
Yeah, I mean, Nihan will explain that.
Right. So just to quickly answer Gopu's question, definitely. So calculating these anisotropy maps is essentially a search for the background. So, and when you're searching for a background, the pulsar term is essentially just an additive noise that can be absorbed in the intrinsic pulsar noise, right? So it won't really add anything more to your data, I think, when you're producing these maps. But when we do our formal searches for continuous deterministic signals, then we definitely need pulsar terms to be included in our analysis. And I'm sure you already know that very well.
Nihan, so what is a pulsar term? It is gravitational waves from pulsars?
No. So the way that we sort of think about the effect that's produced by a passing gravitational wave through a PTA detector is that you can think about the effect that's produced by the gravitational wave when you're at the radio telescopes on Earth. So as well as the curvature in the space-time that will be produced by the wave as it's passing close to the pulsar. So there will be some time difference between when the wave passes at the pulsar and when it passes at the Earth. And so that's essentially what we call pulsar term and the Earth term. So it's just a slight phase difference between the background at the Earth and the pulsar. When we are searching for the background, like I said, it can essentially be absorbed as a noise term into the individual pulsar red noise, so we don't really need to worry about it. But when we are talking about looking for deterministic sources, we do need to include it.
Are you not missing then some signal if you absorb it into a noise? It seems to me pulsar term is a signal, right? Or is it so indistinguishable from noise?
For deterministic sources, it does add more information about the evolution of the source that we're looking at. But for a background search, it really does not add any more information, since you're looking at just the background, which is a stochastic statistical process. It's just at a different time. And you don't really expect the background to vary on such short time scales. So it can be included in the pulsar noise without loss of any information.
Okay, thanks.
Okay, so where do we go from here? So we have all of this information from the 12.5-year data set. And like I said, so the key quantities that we want to see how they evolve as a function of time are the two-dimensional spectral index and amplitude posteriors to be able to infer the source of the gravitational wave background. We want even before that, actually, we want to know when the Hellings and Downs correlations will become statistically significant in our data set so that we can actually claim a detection of the background. And then finally, we want to see when we can actually begin to probe the presence of any kind of turnover in our data. And so let's see how much. Oh, we only have about 15 minutes left. So what I'm going to do is I'm going to skip over this particular part of the talk. And just to quickly summarize what I wanted to say here is that in simulating the PTA datasets, what we do is we ensure that the simulated dataset that we've generated is very identical to the NANOGrav 12.5-year dataset. So we use the same pulsars that were in the NANOGrav 12.5-year dataset, shown here in this figure on the left. What we do is we use the noise properties that were measured for the pulsars in that analysis, and we inject them into the simulated pulsars. And finally, we extend the total baseline of the simulated dataset out to a maximum of 20 years. And we do this by using the cadence of the observations in the last year of the observations for all of these pulsars in the 12.5-year dataset. So that ensures that the data set that we're creating is almost identical and is a perfect sort of perfect scenario, perfect case, or perfect or ideal case PTA data set. And what we do is once we have this data set ready with us, we inject both pure power law and realistic background spectra into this simulated data set, and we vary the amplitudes of the injected backgrounds in the range of 10 to the minus 16 to 5 times 10 to the minus 15. And this range was chosen to represent the realistic range of amplitudes that's expected for a stochastic gravitational wave background. And for the realistic injected spectra, we inject 3 different types of spectra. One which really does not have any turnover at low frequencies, which we label negative because the derivative with respect to frequency at low frequencies is negative. And we also inject spectra where there's noticeable flattening at low frequencies, labeled as flat, and a significant turnover at lower frequencies, which we label positive. And those 3 spectra are shown in the figure on the left. And these were created using cosmological hydrodynamical simulations from Luke Kelly, who was generous enough to produce these for this analysis. And finally, what we do is we generate 10 realizations of these gravitational wave background spectrum and dataset, and we pass each of these 10 realizations with each of the injected amplitude and each of these spectra through our entire standard detection pipeline. And we see how the signal evolves in the PTA dataset as a function of time.
Nihan, if I may interrupt. So I just wanted, I had 2 questions. First of all, these 10 realizations, they differ in terms of only the amplitude or some other parameter. And the second question was that this injection is done in the residuals, or so where exactly in your analysis you are injecting the power law or the spectra?
Right. So for the first question, we have 10 realizations for each of the injected amplitude. So each amplitude has 10 realizations, and in each realization, there's sort of small differences. There's essentially small stochastic differences between what we inject and just added quadrature noise on top of that. Right. So that's what we mean.
So where do you take the a priori distributions of the amplitude? So to get those realization, you need to assume some distribution, right? So what is the assumed distribution there?
Not exactly. So to generate the different realizations of the data sets, what we do is we just vary the parameters around the injected values. So it's essentially a random deflection around the injected values.
Okay, so it's just normally distributed around the injected value. Okay, thanks. And the next question was about where do you inject it, in the residuals or somewhere else?
I think it's in the TOAs as just a red noise process on top of the intrinsic red noise.
Okay, so the data set which you generated and extrapolated to 20 years, in the TOAs you just inject whatever you get out of these spectra, right? Is that correct?
We inject so in the case of the realistic spectra, we inject the full spectrum. So this is using libstempo, if you're familiar with it. And then you have the option of just injecting either a custom manual made spectrum, like the 3 that we have on the left, or you can just inject a pure power law spectrum where then you just specify the amplitude at a frequency of 1 over a year and the spectral index.
Okay, so this is tempo 2 injection. Okay.
Yeah.
Right. Okay, thanks.
Mm-hmm. Right. I apologize because we only have 10 minutes, and I do want to get to the part about the IPTA because I think that's the most important part of this talk.
Okay. If you want to take
can we go for
10
more additional? There are lots of questions, so can Nihan take a bit more time?
Yeah, sure. 10-15 minutes over.
Yeah.
Is okay.
So Nihan, take your time. 15.
Okay.
So you can, something like 11:45, 40 plus.
Okay.
Thank you.
Okay. Awesome. Thank you very much. Yeah. So, like I said, once we have these all of these realizations and injections of the data sets ready, we pass them through our standard detection pipeline and see how the signal evolves in our data set. And so before we do that, we actually had to devise a new statistic to quantify the PTA milestones that we define in this paper. And so we define a new statistic called the total signal to noise ratio, which is the log likelihood ratio between a model which has the gravitational wave background plus noise versus just noise only. And the reason that we had to develop this new statistic is because the typical Hellings and Downs cross-correlation signal to noise that's usually quoted in the literature, while it's absolutely indispensable as towards confirming whether a signal is truly astrophysical gravitational wave background, it does not really capture the full information in the background signal, because it essentially ignores the information in the autocorrelation terms, because it's based on the calculation of the cross correlations. And since it's not accounting for the full signal model, it does not really completely reflect the presence of the signal in the data. On the other hand, this total signal to noise ratio accounts for both the autocorrelations of the gravitational wave background as well as the cross correlations. And so it accounts for the full signal model. And there was this great analysis by Romano et al. Published a couple of months ago that also looked at this subject, and they showed that the total signal to noise, which when you account for this autocorrelations, is always going to be greater than the Hellings and Downs signal to noise ratio, because the autocorrelations tend to contain most of the power from the gravitational wave background, at least at early times. And as I've been saying, that a Hellings and Downs cross-correlation signal to noise ratio of 3 is what's necessary to claim a detection of a astrophysical background. That Hellings and Downs value of 3 corresponds to a total signal to noise ratio of about 25. And so that's just a reference that I wanted to keep in mind as we move ahead. So here on the left-hand side, I'm showing the evolution of this total signal to noise ratio statistics, rho hat. And on the top left is the evolution of the statistic as a function of the injected amplitude, which is shown on the y-axis, and as a function of the timing baseline, so the length of your data set on the x-axis. And it's pretty much as you would expect. So with a stronger injected amplitude, this total signal to noise ratio statistic grows as you would expect. And as you increase the length of your data set, this statistic also grows as you would expect. And the black star here represents the range of the recovered amplitudes from the NANOGrav 12.5-year analysis. And similarly, on the bottom left is showing the slice at an injection of 2 × 10⁻⁻15, which is slightly larger than the detected amplitude in the 12.5-year analysis, which remember was around 1.9 × 10⁻15. But we still see that the prediction from our simulations for the value of rho hat, for the total signal to noise, is completely consistent with what we are seeing in the real NANOGrav 12.5-year dataset. And here comes the...
So this is assuming the current population of pulsars.
I'm sorry, could you say that again?
So this is assuming the current known pulsars that you are using.
Yes, so this
is
just...
if you have more pulsars in the future, how fast will it improve?
Yeah, that's a great question. So first, you're absolutely right in that we are just using the 45 pulsars that are in the 12.5-year analysis, and we do not add any new pulsars to this analysis as a function of time. So even at the 20-year baseline, we still have the 45 pulsars from the 12.5-year analysis. As to your second question, as you add more pulsars, the total signal to noise grows correspondingly. So it's not directly proportional, but it's actually proportional to n to the power of 1.7. And so it grows significantly as you add more pulsars to the array. And I'll touch upon this once more when we get to the IPTA.
And according to this plot, you will reach this signal to noise of 25 that you said that is necessary to detect the cross correlation in 20 years.
No,
right?
We are actually very close to that. So
we are close to 20. Okay.
Right. So the reference value that you're looking for is 25. And so the NANOGrav 12.5-year analysis is very close to that. So it's around 2021. So yeah, I'll get to this in 1 minute. It's on the next slide. Okay, so as I was saying, so while even though we might get to a total signal to noise value of 25 within a year or a year and a half worth of data, that's not really what we can use to claim a detection of the background, because that really, while it does encode information from the cross correlations, it it is not solely based on the cross correlations. And for that, we again have to come back to the Hellings and Downs cross correlation signal to noise ratio, which is shown in this plot on the bottom left. And so in the red shaded region is the evolution of the Hellings and Downs cross correlation signal to noise as a function of time. And we can see that this grows almost proportionally. This grows as we increase the baseline of our pulsar timing array dataset. And again, what we are seeing with the 12.5-year analysis is consistent with what we are predicting in our simulations, though it's consistent at the relatively lower end of the predicted range. And the shaded regions here are 95% confidence intervals. However, in predicting when we would make a robust detection of the gravitational wave background based on the Hellings and Downs correlations, what we did is that we did not just look at when we would achieve a Hellings and Downs signal to noise of 3, but what we did was we looked at when the Hellings and Downs correlations would become more significant than the other two types of correlations that we typically look at, which are monopole and dipole. And based on the plot on the bottom left, we see that these Hellings and Downs correlations can become significant in our data set anywhere between the 15 to the 18-year baselines. And so based on this, what we predict is that we expect to see a significant detection of Hellings and Downs correlations in our PTA dataset, even if we just stick with the 45 pulsars, somewhere around 15 to 18-year baselines. And just a reminder that right now we release the 12.5-year analysis. So somewhere either in our next data release or the one after that, we should have statistically significant evidence for Hellings and Downs correlations. And on the top left, I'm just showing the evolution of the cross correlations as a function of the angular separation. And we can see that as the signal to noise for the Hellings and Downs correlations increases, we can see that these points sort of coalesce around the theoretical Hellings and Downs curve. Though if you look at the error bars on these points, there's still room for deviations from the theoretical Hellings and Downs curve in these angular cross correlations.
So Nihan, so you said next data release, so you're releasing data every 2 or 3 years?
Yes. So yeah, that's the expected timeline as of now. Yeah.
And this 12.5-year data is now public. So what kind of data is public? So is this the time series or the residuals?
So with the 12.5-year data set, which is now public, we release the full time of arrival data set along with the timing model for all of the pulsars. And we also release the results from our noise analyses that were done as part of the 12.5-year analysis.
And is also some software also made public to analyze this data?
Yes, all of our detection pipeline software and code is public. It's hosted on GitHub, and I can send you the links to that, or I'm sure Goku or Bhalchandra already knows where you can find it. So they can also easily guide you if you want to take a closer look. And if you have any questions about those, feel free to reach out to me at any time.
Okay, thanks.
Right, so once we have a robust detection of the gravitational wave background, which is sort of our first milestone here, we can move on to the second milestone, which is determining the source of the gravitational wave background. And as we saw earlier, this is really dependent on the fractional uncertainties that we can get on the amplitude and spectral index of the gravitational wave background. And so what we saw in this analysis is that you can create a very nice relation between the fractional uncertainty on the amplitude and spectral index as a function of the total signal to noise ratio rho hat. And that's what's shown on the plots on the top left and bottom left, along with the fractional uncertainties in the 12.5-year dataset. And so based on our simulations, we predict that once we are at the point of detection of a gravitational wave background, we expect to have fractional uncertainties of at least 44% on the gravitational wave background amplitude and at least 40% on the gravitational wave background spectral index. And this level of accuracy is sufficient to distinguish a supermassive black hole binary origin for the gravitational wave background from some models of other more exotic sources, but not all of them, because there's a huge variety in other source models that have been predicted. And so we would need to wait for the PTAs to increase in baseline length to get even better fractional uncertainties on the spectral index to be able to conclusively reject these other source models. And finally, we haven't really talked about the amplitude uncertainty too much, but the fractional uncertainty at the time of detection will also allow us to arbitrate between some models of the supermassive black hole binary population itself. So these models were used to make predictions about what the amplitude of any gravitational wave background by supermassive black hole binaries would be. And so having a spectral index uncertainty of 44% on the amplitude would allow us to distinguish between the Sassana 2016 model and other models which predicted relatively higher amplitudes compared to that, which are the McWilliams et al. Model and the Simon and Perks-Flower model.
Nihan, I thought Sean's model is essentially ruled out in the sense that we have not, I think he was talking about detection, significantly higher, right? Or he has some freedom to choose the parameter to bring it down to?
That's right, but it again boils down to the fact that we have to wait until we actually claim a detection of a background before we can say that this model is rejected, right? So okay. It's a little bit of semantics at this point,
right?
But you're completely right.
Thank you.
Okay, so this is our second milestone, and finally, once we have the source of the background, we want to start measuring the properties encoded in the gravitational wave background spectrum. But before we get to that, we wanted to test whether the presence of a spectral turnover in the gravitational wave background will inhibit the detection of the background in any kind of form. And so to investigate that, what we did was we looked at how the total signal to noise ratio evolved as a function of time for all of these three realistic injected spectra, and we compared it to that of the pure power law injection, which is shown here on the left-hand side. So the set of curves that are shown on the plot on the left represent the 95% confidence intervals on the total signal to noise returned from these realistic injections. And what we found was really encouraging in that between the 15 and 18-year slices where we expect to make a conclusive detection of the gravitational wave background, there is not a huge difference in the significance of the signal based on what kind of turnover is present in the background spectrum. So even if there was a strong turnover in the spectrum, it would still not stop us from making a conclusive detection of the background within the time frame that we stated in this analysis. However, we would begin to see some sort of plateauing of the significance of the signal as we get to longer baseline, where we just don't have enough signal at the lower frequencies because of the presence of a turnover. And then we would really begin to see deviations from the expected growth of the total signal to noise ratio. So given that given the good news that we would still be able to make a detection despite the presence of a turnover, we wanted to see when was the earliest that we could start making statements about the presence of this turnover in our dataset. And to do that, like I said earlier, we make use of the full spectral or the free spectral model, which is shown here on the left. And the different colors represent the different points represent the different types of realistic injected spectra. And the solid lines represent the injected spectra. And so we can see that, and so the plot on the left is shown for a timing baseline of 20 years. And it turns out that it is that we likely would need at least 20 years worth of data to actually begin to see any kind of deviations away from a pure power law behavior when modeling the full spectral model for the gravitational wave background.
So Nihan, at high frequencies, your recovered points are much higher than what you injected.
Yes, and that's because at high frequencies, we are mostly dominated by white noise. And so that's where you're seeing this upwards trend that you talked about earlier in the talk. And that's because we're just looking at at this representation in characteristics train space. And so that's where we are dominated by white noise, and the background spectrum is just too weak at those high frequencies to actually register in those high frequency bands.
Nihan, how many bins you will require to see the turnover in low frequencies? At least 3, 4, or?
I think at least 3, 4. You could kind of start to you would begin to see hints of deviations from pure power law with just maybe 1 or 2 bins, but to actually train like Gaussian processes and actually recover the turnover correctly, you would need at least 3 to 4 bins. And I just want to say that we are doing a follow-up analysis where we look at this exact question and try to answer what conditions we would need to accurately recover the turnover.
Okay. There's a question, maybe we can take it later. Please go ahead.
Right. So this brings me to the importance of the IPTA. And so just a quick recap of what the IPTA is. I'm sure a lot of you are already familiar with it, but the International Pulsar Timing Array combines the times of arrival datasets collected by individual PTAs around the world into a single collective dataset. And so the current PTAs around the world are the North American PTA or NANOGrav. There's the European Pulsar Timing Array, the Parkes Pulsar Timing Array, the Indian Pulsar Timing Array, which I think a couple of weeks ago became a full voting member of the IPTA. So huge congratulations about that. So NPTA is the newest member of the IPTA, and other emerging PTAs around the world are the South African PTA and also the Chinese PTA. And there's a lot of benefits to combining the data from constituent PTAs into this International Pulsar Timing Array. And I will get to all of those in a second, but I wanted to center this discussion around the latest data release coming out of the IPTA. And that's called IPTA DR2 or Data Release 2. And this data release has 65 pulsars in it compared to just the 37 pulsars that were present in the constituent data, in the constituent NANOGrav dataset that went into actually building this IPTA DR2 dataset. And even if you compare these 65 pulsars to the latest NANOGrav 12.5-year result, you will see that even in the 12.5-year result, we had just 45 pulsars in our analysis. So this is even a step up compared to our most recent GWB analysis. So the plot on the left shows the distribution of the IPTA DR2 pulsars on the sky. And in the red points are the pulsars that were present in IPTA DR1. And the blue points represent the pulsars that were added in DR2. And so apart from the benefit that comes from just having such a high number of pulsars in your PTA, an additional benefit of combining, excuse me, of combining these pulsars from the PTAs all around the world is that this opens up the possibility of observing the entire sky, right? So for example, with NANOGrav, we can see all of the northern sky, but there's a huge chunk of the southern sky that is just not visible to us. And the reason that it's better to have more pulsars on the sky and to have them more uniformly distributed over the sky is that we need as many pulsar pairs as possible to be able to calculate as many of those cross-correlation coefficients as we can. And that helps us to better characterize the Herring's and Downs cross-correlation coefficients. So having at least from a North American perspective, having the entire southern sky open up to us through the IPTA is very valuable, and which would just be very difficult to do in using telescopes in North America. So to show how much better the IPTA is compared to any individual PTA, what we did was we used the times of arrivals from the IPTA DR2 dataset to model its sensitivity and compare that against the sensitivity of the constituent NANOGrav 9-year dataset that, like I said, went into building the IPTA DR2. And And we did this using the Hasasiya software that was released with this great work by Hasmoon et al. in 2019. And so the sensitivity curves that came out of this analysis are shown on the plot on the left. And we can see that the IPTA DR2 curve is just hands down better than the NANOGrav 9-year dataset at all frequencies. And it's just more sensitive even at higher frequencies, it's more sensitive at lower frequencies. And what this sensitivity translates into is that the IPTA DR2 turns out to be better than the NANOGrav 9-year dataset by a factor of 30 in terms of recovering the total signal to noise ratio, by a factor of 4 in terms of improved fractional amplitude uncertainty, and a factor of 5.5 for improved fractional spectral index uncertainty. And this is just really great. Like this accelerates our timeline to get to all of these science results that we talked about earlier, just much quicker with an IPTA style data combination. And it's not just that, but under the data combination of the IPTA, we also have significantly longer baselines for some of the pulsars in the PTA. So for example, in the DR2 analysis, for some of the pulsars, we have baselines which are as long as 20 to 30 years, which is just amazing. And it unlocks much lower frequencies than would be possible with some of the constituent PTAs. And what that allows us to do is that once we are probing these low frequencies, it just makes our life easier when we're looking for more complex structures in the gravitational wave background spectrum, like the turnovers that we've been talking about earlier in this talk. And finally, just this acceleration in terms of the increase in the significance of the signal also means that we can get to results like probing for anisotropy in the background much quicker than would have been possible with just any single PTA dataset. And so combining individual PTA datasets under the IPTA dataset is just going to accelerate the science that we can do with PTA with PTA detectors significantly. And just a few final words, apart from everything that I've already said about why the IPTA would be better, is that the data sets that come together under the IPTA also have a broader range of frequencies with better instruments that might be available for any single PTA. So for example, with the Indian PTA now coming into the IPTA, the IPTA now has the GMRT as part of its large suite of telescopes. And I think it's one of the best instruments in the frequency ranges that it operates in. And that's going to be very, very useful for us in modeling the chromatic red noise that's present in a lot of our pulsars. And that's going to be really invaluable when we eventually move towards a detection of a gravitational wave background with the IPTA. Like once we have modeled all the intrinsic noise with great accuracy, then we can trust the amplitudes and spectral index that we are recovering for the common process even more. And so this broader range of frequencies that's covered with the IPTA allows us better advanced noise modeling of pulsars in the IPTA. And finally, one of the unique features of the IPTA collaboration is that it also provides us unique opportunities for cross-validation of any detection of a gravitational wave background. So by cross-validation, I mean that what we can do is we can analyze each of the constituent data sets separately and search for a background in all of these data sets, and then put them all together and analyze the IPTA data combination for a gravitational wave background. And we can use all of these analyses as cross-checks against each other to see whether they return results that are consistent with each other. Because if they're not, then that might highlight a problem with one of the constituent data sets or something that might be out of sync between different PTA results. And so this is a unique opportunity for cross-validation of any detection of a background or even a deterministic signal for that matter. And finally, the better sky coverage that's offered with the IPTA is also very important for detection of deterministic gravitational waves, such as gravitational waves from individual supermassive black hole binaries. So when looking for these deterministic gravitational waves, it's more important to have pulsars close to or directly along the line of sight of a potential host for these supermassive black hole binaries. So, for example, if you think there's a supermassive black hole binary somewhere in the Virgo cluster, then it would be useful to have a pulsar that's close to the line of sight to the Virgo cluster, and it's even better if you have more pulsars, if it's more than just a single pulsar. And so, just naturally, given the better sky coverage of the IPTA, this then further enhances our chances of detecting these deterministic gravitational waves. And so I just leave this summary up here, and I can take questions. But the take-home message from this talk is that PTAs are very well placed to make a conclusive detection of the stochastic gravitational wave background in the next several years. And a detection of this background will either confirm the existence of supermassive black hole binaries in the universe, or it will reveal some other exotic process that was just completely unknown up to this point, and we would be seeing it for the first time in our PTA datasets. The paper that describes all of the results that I've talked about and some more details as well is up on archive. I would recommend you wait a day if you want to dive in and read it. I'm going to upload a new version corresponding to changes that I've made from our first draft report. But the paper is up on archive, and yeah, I'm happy to take questions.
Thank you very much, Nihan. And this was our Bible 20 years ago, so I'm happy to see the book title again. So there was a question. I will in the chat. I will read out again to you. It's from Carter, and he says that in the figure of the HT curve, doesn't it contain information that autocorrelation doubles the power?
Yes. So indeed, if autocorrelations do have twice the amount of power as compared to any of the angular separation bits, right? That's just a consequence of the Helings and Downs correlation, the Helings and Downs correlations. So yeah, that's absolutely right.
So I have a question on Helings and Downs. I mean, so this is obviously the quadrupolar, but what kind of signal to noise ratio you will require if you want to go beyond the quadrupolar in general relativity? For example, you can consider post-Newtonian, and so you have, not just the quadrupole gravitational waves, but you have octopole contributions and all that. Is that anyone thought about those? In your analysis, it can be answered?
Right, so we haven't thought about this in this particular analysis, but what I will tell you is that keep your eye out for a paper coming out from NANOGrav very soon, in which we've looked for alternative polarizations. So the quadrupolar correlations come out from just the TT mode, I think, from GR. But in this paper, we are also looking at other modes of cross correlations in our 12.5-year data set. And so keep an eye out for that. I would, yeah. That's honestly, that's all I have to say about that, because I'm honestly not an expert in alternative theories of GR. So I can't.
No, I'm not thinking about alternative theories. Of course, if you can have different polarization, there are longitudinal modes and other than the transverse, I understand. That's the different. I mean, here we are talking about in GR, but it's not just the quadrupolar. So if you have seen recent, so the higher modes, they can also create correlation, but it may require substantially high signal to noise ratio. That may be I can imagine that, but I don't know the numbers. That's what I was asking.
Yeah, I don't know if we've ever quantified what would be required to see the octopoles, but one thing that we've been looking at recently is doing a Legendre decomposition of the cross correlations. And so in that sense, you can kind of directly look at what what significance you're seeing in the octopole, which would, I think, be L equals 3. The quadrupolar is L equals 2, and right?
Correct.
Yeah, so I would say stay tuned, because we haven't done any kind of quantitative analysis on this, and it's something on our collective to-do lists, but I don't have a good answer for you for that.
No, thank you. I have one more question before others walk in with their questions. I mean, there were several questions. So again, I will go back to Steve's paper. I have to read it. What I was thinking about is that if there's a pixel which you may associate with an, somewhat a bright source, not that bright, so that will constitute an anisotropy for you, right? In the background.
Right. So
okay. Yeah. So my question is that's fine. That's the way I'm also thinking about. But in that pixel, maybe correlated. If you incorporate pulsar term, at least on some of the, because this pixel is associated with certain location. So if you associate pulsar terms on a bunch of nearby, as you correctly pointed out, what you will find that the background, this pixel may have, cousins in the neighborhood, which will help you much faster. That's simply coming from the pulsar terms. That will be, that's the kind of thing I was thinking about. I don't know how to quantify it, but my point is that the extra pixel, I mean, because you ignore the pulsar term, ideally this pixel should have some nearby pixels due to the pulsar term, which you have been ignoring in the name of background. So that's what I was thinking.
Yeah, you're absolutely right. And I did not mean to say that constructing these anisotropy maps is the one and true way to find these not single, but deterministic sources, right? It would be sort of a first hint as to, okay, there seems to be excess power coming from this pixel or this part of the sky. And then we could go back in and sort of do our usual batch of continuous wave searches where we would include the pulsar term, like you said. So this is by no means the one true method for detecting continuous waves, right? It's nothing like that. It would just give us hints through the anisotropy that we can expect to see something more than the background in our data, right? That's all I meant by using it.
Thank you. Girish has a question. Girish, please go ahead.
Yeah, it was a very nice talk. Thanks. So I'm Girish Kulkarni. So I had a couple questions. It's just trying to understand some of the issues here at smaller timing baselines. So at baselines below 10 years, what are the problems and opportunities there? You clearly have what you have been calling white noise at those scales. What is the source of this noise?
Right. So let me answer your second question first, because I think the first one was slightly broad, and I'll come back to you about that. But so what I mean by white noise is essentially noise that is not correlated in time. So white noise is not correlated from one epoch of observation to the next epoch of observation. So the kinds of noise that would qualify as white noise would be something like instrumental noise, or just random jitter in the pulsar's emission, or something even like correlated noise across radio frequency, so for example, you have standard dispersion measure, right? So it's correlated across frequency, and if you've modeled it correctly and there's no variations, which is never true, then you would think that it's just on that day, right? So by white noise, what we mean is essentially temporally uncorrelated noise. Does that answer your question?
Is there any hope of beating that down with maybe?
Yeah, absolutely. So one of the solid ways to beat it down is to increase the cadence of your observations. So the more frequently you observe, the better you do at quantifying this white noise and sort of beating it down. And that's something where the IPTA comes in very useful, because no matter what you do, you're always going to be limited by the amount of time you're awarded on any given telescope. And so if you have just one telescope in your PTA, then there's going to be natural limits on when you can observe and how much you can observe. But with the IPTA, you have a bunch of telescopes that are observing some pulsars that are common among different PTAs. So you naturally have a higher cadence on a lot of these pulsars. And so that's one really good way of beating down the white noise. The other way of beating it down is just making sure that we quantify all of these different processes as best as we can. So modeling the ISM, the dispersion measure correctly, modeling higher order ISM effects correctly, all of that can help us in beat down the white noise. And it is important to beat down the white noise because we expect some deterministic continuous wave sources to be present at the higher frequencies. So by that I mean the binaries that have been predicted to host supermassive black hole binaries just based on their EM observations. So for example, 3C66b, OJ287 might be one of the candidates, but it seems a bit too far away. And you can chat to Goop about that. I'm sure he has lots to say about that, but we have a few other candidates as well. I think PKS 1012 is one of the newer ones. But yeah, it's super important to beat down the white noise.
And these baselines are they interesting from the perspective of physics as well? These source models that you discussed, because I got an impression that at those frequencies you didn't have much variation between different models. Is that correct?
Right. So at these high frequencies, you're not really interested in the background anymore. You're looking at these individual sources. And so what you can do is essentially all of multi-messenger astronomy on these sources, right? And Gopu is an excellent person to talk about this because he does this a lot. And honestly, he might even be a better person than me to explain this, because I myself don't do a lot of multi-messenger astronomy right now. And I don't do a lot of deterministic gravitational waves right now as well. So I would
and then Nihan, so thanks for that. And then just without taking too much of your time, I'll just quickly ask one other question of the earlier part of your talk, which is, I mean, this is something I wanted to ask Steve as well last time, but what is a very brief response from NANOGrav at the moment for the presence of a common process correlation and the absence of a Hellings down correlation? How are you interpreting this at the moment?
So the way we are thinking about this for the 12.5-year data set is that it's a common process. It's a spatially uncorrelated common process. So the spatially uncorrelated part of it is that there's no Hellings and Downs correlations. And by calling it a common process, it's evident in a lot of our pulsars. But like I said, without the Hellings and Downs correlations, we cannot claim a detection of a background. So we cannot say this is a background at any rate in the 12.5-year data set. And so we don't do that in the paper either. And
it is not inconsistent with background also. It could be background.
No, but I guess a related concern is also that that your common process correlation is also not visible in all of your pulsars, right? It's only visible in a subset. So I think that's what making it very difficult for outsiders like us to understand how to think about this.
Yeah, and that's always going to be true to some extent, that we will see the common process in only a subset of the pulsars, just because you need. So for example, you're much more likely to see this process in pulsars where you have a timing baseline of like the full 12.5 years, right? Because this is a really long period. Excuse me, this is a really long period process. But you're less likely to see it in pulsars that have relatively shorter baselines. So if a pulsar has a baseline of 3 years, then you're less likely to see it just because you don't have the sufficient baseline span to become sensitive to these long period processes. So to some extent, that's always going to be true. But as the baselines of these data sets grow, we should expect to see more and more of the pulsars begin to favor this common red process.
I see. Okay. Thank you. Thanks.
I just want to add one comment. For example, the fast pulsar timing array, I mean, the Chinese pulsar timing array, because of the sensitivity of the fast and short duration of their, span of their observation, are going to be That's what we have been told. It will be sort of a complementary because of the sensitivity and all that. It will be high frequency. Of course, they will eventually contribute to the IPTA, but they will be very unique in the high frequency. So that's something to look forward to.
Yeah, absolutely. And sorry, just to add real quickly to that, even the South African PTA with Meerkat right now, and then eventually the SKA, it's just going to blow all the radio telescopes out of the water. And based on some early results, it seems like we would just, like Meerkat will just blow everyone out of the water. Like it's going to be amazing.
That's true, yeah. Okay, thank you. One more question. This is from Abhimanyu. Abhimanyu, please go ahead.
Yeah, so what is the difference between E-core and the other white noise parameters you have mentioned in this slide? So what exactly is the origin of E-core?
I actually don't know. Well, I think it was, what was it? Was it EFAC and E-quad that was in the original PTA paper, or I forget. But what E-core stands for is essentially noise that's correlated across radio frequency, but it's not correlated across different observing epochs. So it's per epoch radio frequency correlated noise. Whereas on the other hand, EFAC is kind of a scaling factor for the TOA uncertainties that you derive out of your timing packages. And E-quad is additive noise that could be from instrumental effects or jitter effects or other random processes like that. Does that answer your question?
Yes, yes, thank you. So what is the reference for this thing?
I think a good place to start would be the NANOGrav 9-year data, the NANOGrav 9-year GWB analysis paper, and then going through all the references in there.
Yes, thank you. That answers my question.
If you have no further questions.
Yeah, I have a question.
Okay, go ahead.
So Nihan, so I have just a basic question. So you are measuring the time of arrival of pulses from the pulsars. So what is the accuracy that you need usually on individual pulsar timing, individual pulse timing?
Right. So let me go back here. So since the delays that are being produced by this common process are around a microsecond or so, right? So you need accuracies, the TOA accuracies, or I should say your RMS uncertainty on your residuals should be of the order of microseconds or hundreds of microseconds.
Okay.
If you get above hundreds of microseconds, then it's not going to be a good timer, I think.
Okay, and this is much smaller than the individual size of the pulse, right? Pulse is of order millisecond. What is the width of the pulse?
Yeah.
Okay. So then this the change in the shape of the pulse because of propagation through the ISM, that is a source of error.
Yes, it is. It is a source of noise.
So if the pulse becomes broadened, then you cannot really measure the edge of the pulse accurately. So
yeah, that's true. So as you move towards lower observing frequencies, lower radio observing frequencies, your TOAs correspondingly get larger. Your TOA error bars get correspondingly larger because your ISM effects scale as f to the inverse power of at least 2. But then if you have higher order effects, then you have more, right? So yeah, that's it.
Okay, a practical question. So when a pulse comes and you detect it in your radio telescope, so do you use this whole pulse shape to get the TOA, or do you look at a particular edge, like a leading edge or trailing edge of the pulse, to get this TOA? Or do you use the whole pulse shape?
Yeah, I forget what we do. I think it's so there's two answers to this. In the standard way of doing things, I think we use, I'm not sure, the leading edge or the trailing edge, one of the two. But there's also an alternative way of doing pulsar timing, which is called profile domain timing, which was led by Lindley and Tati et al. As part of the European PTA. And then you would actually look at the full shape of of the pulse profile and then use that to produce TOAs and TOA error bars. So you can do both of these to produce TOAs.
So this is your 12.5-year results. Which method are they based on?
So they are based on, so they are not based on profile domain time. So it's a standard way of timing.
If you use profile domain timing, then do you expect some improvement? Maybe. So are you limited by this time of arrival errors, or are the main source of error something else? So you can find a method to improve this. Will it help?
Right. So we do account for changes in pulse profile shape in a variety of different ways. So for example, we include what's called FD parameters, which model the evolution of the pulse profile as a function of frequency. We also check for pulse profile variations as a function of time. And Paul Brook from NANOGrav had a paper about this, I think last year or the year before that, where he looked for pulse profile variations in, I think, our 11-year or 12.5-year data set. I don't remember. It's getting late for me. But yeah, we have all of these techniques already developed to account for these changes in profile shapes. So
these are used in this result, 12.5-year result, or no?
I'm sorry, could you say that again?
All these techniques, are they used in this 12.5 years result, or?
Yes, they are. And you can check the 15-year dataset paper to get a list of everything that we've done with this.
And all these pulsars, so a single pulsar, is it monitored only at a one frequency or at many frequencies? So at many radio wavelengths.
I mean, the radio emission from pulsars is broadband. So it's across, well, it's not across the full radio band. But
the observations, are they being done at a particular frequencies? Like you only look at one or two frequencies of each pulsar, or is there many more?
So we need to look at least 2 different frequency bands just to be able to model ISM effects. So in NANOGrav, we look at, right now we are looking at the 800 megahertz band, and we also look at L band. We are doing some observations at S band now with VLA.
What is the frequency of L band and S band? Sorry, I am not familiar.
So L band is not around. L band is centered at 1400 megahertz. S band is 3200 megahertz, I think.
It's about 4 gigahertz. Okay.
Yeah, that's right. And with CHIME, which is a new telescope in Canada, we are also beginning to incorporate that, and that observes at lower frequencies of around 400 megahertz.
So in the future, if you are observing more and more frequencies on each pulsar, that should also improve your timing model and ISM effects. So that should also lead to increase in your signal to noise.
That's precisely what Palchandra and our team is doing.
Right.
We do simultaneous observation.
Yeah. These improvements are not included in your projections that you showed.
Those will happen.
No, those will happen in future. So Rishi, just to answer your question, just to give a comment there. First of all, the time of arrival is done in frequency domain by taking the Fourier transform of a standard template and cross-correlating that Fourier transform of the standard template with the profile template. Okay, so you do a Fourier decomposition, and that is how you get the time of arrival.
Okay, so that way you are taking into account the full shape of the pulse.
It's the full shape which is going into the picture. But the cross correlation is done in the frequency domain to sort of get this is a method which was evolved by Joseph Taylor and others long back. There are a few other methods also to do this, and there are about 6 different algorithms which are used for doing this, and all of them, as Nihan said, go into the NANOGrav data. The second question is, yes, the wider the frequency coverage, the better is the precision which you can get from the PTA data series. Most of the NANOGrav, as Nihan pointed out, was 800 megahertz and above, except for a very small band of frequencies from 300 to 340 megahertz using Arecibo telescope, which unfortunately is no longer there. And similarly, the Parkes experiment uses 800 megahertz and above, and they go right up to 4 gigahertz and so. So there are broadband observations which are happening on these. Once GMRT data goes into the IPTA, as Nihan mentioned, we would be covering everything from 300 megahertz upwards to 800 megahertz. And that should allow a much better characterization of the interstellar medium effects and also improve the precision. So one of the improvement in the NANOGrav set which has been done is called as wideband timing. Okay, so there is a technique generated by worked out by in a great paper by Tim Penucci and collaborators, and that in the 12.5 has shown remarkable promise. And if we apply that to wideband things at lower frequency from 300 to 800, that should also improve the precision of the data set significantly. So the short answer to your question is, yeah, the more the frequencies, the more the telescope, the more the different PTAs contributing to IPTA, the faster is the chance of detection of gravitational wave. I think that was the point which Nihan was making also. Yeah.
Yeah, absolutely. And just to add a little bit to what Bhalchandra just said, so there's also a new class of backends coming online called the ultra wideband receivers, which have a ridiculous bandwidth from like 800 megahertz all the way up to I think 4 gigahertz or 2.6 gigahertz, which I think Bhalchandra also just mentioned. Now that I think about it, but even when these backends come online, the GMRT system is still going to be unique because it still covers a frequency range that's not covered by these ultra wideband systems, and so there's still going to be a unique place that the Indian PTA can occupy in the IPTA.
What is the highest frequency these pulsars you can detect? Can you go up to, for example, CMB band like?
No. So Rishi, the spectral index of the pulsars is very steep. Okay, it is the typical average spectral index for these millisecond pulsars is about minus 1.8, which means as you go to higher frequency, they become weaker and weaker. So I guess 4 gigahertz, 5 gigahertz is about the best which you can go to. You probably will not have very good timing precision. So as the pulsars become weaker, the uncertainties on the time of arrival also become worse. So you can't actually go beyond 5 gigahertz. So typically, I think most of the experiments focus up to 5 gigahertz and not beyond.
I think we should release Nihan.
Yeah, it's getting very late.
It's very, very late for him. Thank you very much, Nihan. I think we should also apologize a bit, but wonderful talk. Thank you very much, and really enjoyed. So,
okay. Yeah, thank you for inviting me on giving this talk.
Thank you very much. Yeah. We hope to hear you again soon in the